Didn't do the countdown, so I guess I'm started. All right, here we go. Welcome to Understanding Waves Step by Step. I got you viewing me from the Chromebook. I got it right there on the desk. Right, you're looking at me right there from the Chromebook. All right. I drew a nice pretty wave right here on the board. This is more than one wave. I'm just saying I drew a wave curve over here. We're going to go through the labeling the parts, and you guys know a bunch of the stuff already because you've experienced life before, but now we're just going to clarify that you do know these things, hopefully. And if not, then here you go. Here's the beginning. So the highest point of a wave, just basic definitions we're going to start off with, the parts of the wave. So the highest point right there, I got a little dot already for you. The highest point right there is called the crest. And it's not the whole arch up here, it's just the top point right there is the crest. All right, and then the lowest point, the opposite, the highest point, the lowest point, not the whole bottom trough thing, just that point right there is the trough. I just said a second ago, but just the bottom point is the trough. So T-R-O-U-G-H, the trough. All right, those are the two little maximum and minimum points away from this center line right here. So the center line point's where our next thing is going to be. There's equilibrium or base point or baseline, or resting point. So like if you had a spring or a string stretched out and you just had nothing going on, that'd be the resting point. And then you come along and you grab the end and you shake it. So I'm going to show you what's going on over here with this little demonstration right there. I'm going to do that. But first, if you just had a string and you're going to just all of a sudden shake it away, you're going to take it away from the equilibrium. So I'll write that in there now. Equilibrium. All right, so equilibrium is the baseline. I'm going to put that also in there, same thing, baseline. Both of those are the same thing, just clarifying that. All right, and then if you're going to go from the baseline or the equilibrium to the crest, so from the baseline to the crest, just vertically right here, or from the equilibrium baseline to the trough, that's the same distance on a wave, usually in perfect magic physics land, where the baseline down to the lowest point will be the same height as from the equilibrium baseline to the highest point, and that's called the amplitude. So from here to there is the amplitude. All right, amplitude. Same thing over here, so I'll just draw it again. Right there to there is also the amplitude, All right, and then, so we've done 1, 2, 3, 4, and there's one more part of a wave, the parts of the wave, there's 5. The last one is from the beginning point of the wave to the next same point of the wave. So for me, I have it started, I don't even film my camera over here. I started at the very edge right there. I know I'm on camera right here. So right there is where I drew my picture at the beginning over here, I guess. Yeah, it's right there. Okay, so that's the beginning point of my wave over here. And the next time you get to that point of the wave doing the same thing is one wave. So at the beginning, I'm going up. Right here, I'm going down. So that's different. Even though it's in the same location, it's doing a different thing. So right here, you're going up. Right here, you're going down. Next time you're going up again, that right there going up is the next same point. So from here to here is a wavelength, and that's our upside down Y is wavelength. I'll put that up there too. Wavelength. If you can tell very lightly, I have Disney in the background. Be our guest. All right. The most common way that you see it is from crest to crest, because the one point that's definitely only doing the one thing where you're going up and transitioning to going back down again. So from the crest to the other crest is also a wavelength. All right, so there's our little parts of the wave all defined. All right, now I'm going to show you the cool little, I'm just going to twist you like this. Look at my cool giant TV over here. All right, and then I have a little wrench right here, and I can grab it and I can move it, and I'll send little wave pulses going off to the side. And this is a PhET simulation. I went to the PhET website, PhET, and I just went to I don't even remember what it's called. It's a wave on a string demonstration. All right, and right now I have the tension low. If you make the tension high, you got a nice tight string. It's all stretched really tight. You do the same thing, and now the waves go fast. And then this is me moving it myself. All of a sudden, it's at equilibrium, and then I make it go up. I cause a disturbance where it goes up, and everything goes up, and then I can go back to regular. I'm going to change it to oscillate. Now I got a nice repetitive thing, and I'll make the tension go back down. There we go. When the tension is low, the speed gets slower. So I made the tension all the way low to get a nice, pretty sine curve wave going on. Pause. All right, I tried to pause in the middle, whatever. All right, so there's the equilibrium baseline given to us as the dotted lines, and there's the highest points, and I made the amplitude, the maximum displacement from equilibrium as 1 centimeter. Got my little ruler out. You can see it goes up to 1 centimeter there. And so it's also going to do the same thing below. If I brought my ruler down, I'll just do it. I'll bring my ruler over here and go from the 0 point to there. You see it lines up with the 1. So 1 centimeter below, 1 centimeter above is the amplitude. Just showing that little neat thing there. If I was going to try to measure out what the wavelength is, I have from the very beginning point or from the, I'll do from the crest. All right, so crest right here. I'll just put the meter stick there. All right, so from the 0 all the way over to the next highest point, which is right here, is going to be 1, 2, and a little bit more than a half. So it's like 1.6 centimeters ish. 1, 2, 3, 4, 5, something about that, about 2 each, or 0.2 each little dot, whatever. Okay, so those are all the little parts. I don't remember what I was going to show with that, except for just that it's really good. Oh, repetitive motion. One of our other things is we're in the lab, we're comparing it to walking. That's why it's called understanding waves step by step, because we're comparing the waves to walking. So if I turn on the oscillating pulse and go like this again, right? So all it's doing is going up and down, and sending the wave pulses going out. One of the other cool things about this is that if this was a chain of beads, the actual matter that is making the wave or displaying the wave isn't moving along with the wave. The wave is traveling along this way, but the pieces of the matter / the beads of this are only going up and down. They're not going forward to the right. So the matter isn't moving, but the energy of the wave is moving. And so that's one of our little similarities to walking, is that when you walk, you are repeating, right? You're going left, right with your steps. I hit it with my arm and turned it off. Whatever, it's fine. All right. So that's one of the similarities, is that when you walk, you have repetitive motion. You're going left, right, and that's repetitive motion. And then one of the differences is that when you walk, is that you move matter. You are moving yourself. You are making your matter move, which doesn't happen in a wave. The matter that is moving the wave along stays right there. If you've ever gone out in the ocean and you have like a little floaty tube, or you went to whitewater and you went in the wave pool, or you went in a wave pool, that's what I'm trying to talk about, right? So the water wave goes past you, and if you are in your little floaty thing, the wave will kind of lift you up, and you kind of do this little spin around in a circle motion, and there's all kinds of little animations that I didn't prepare for that, just made this today. So you can just kind of like wobble around in your little tube, and if you get close enough to the beach, the wave will push you, because that's a broken wave. Instead of just a little wave going past you, you get actually pushed by falling down the gravity of the front of the hill, the wave, and kind of makes you move, but whatever. All right. Oh, frequency and period. That's what I'm talking about. All right. So make it go again. Play. Nope, it's frozen. Let's try this and then this. Nope. Just make it restart again. Okay. So frequency and period. All right. So period's the easier one, right? So the time of one wave. So if I go to pulse, I have my little setup the same-ish. No, I have a little bit dampening on there. So no dampening. If I do one pulse, and I have it where it'll just kind of bounce back and forth right now, because I have the side because it restarted. Okay. The period is the time of one wave, how much time it takes for one wave to pass a point. So if I was going to measure the time from right there, like the time it takes for one little wave to go by, I can actually make it do oscillate. And I'm gonna open the end so it'll flow out the window and it'll be all normal again. All right, so the time it takes to do one repetition, so from this going from the highest point back to the highest point would be one wavelength. The time of one wavelength is the period. For this one, the period of that is gonna be, calculator, on, clear, clear, clear. 1 divide 1.5. The period of this one is 0.67 seconds. That's how much time it takes to do one wave. And then the opposite of that, the frequency is going to be how many repetitions happened per second. They're the opposites of each other, inverse. One wave divided by the time is the period, or if you do the opposite of that, you do the amount of time. No, that's the same thing. If you do the number of waves divided by the time, that's the frequency. How many things are happening per second is the frequency. Those are the opposites of each other. Trying to get all my definitions. I got my little notes right here I'm looking down at. And then the next thing is just talk about the formula, all right? So this is going on, what else, all right? You guys have seen, hopefully, in previous physics life, where you have V equals d over t, and this is a no acceleration, constant velocity, so no acceleration, nice basic equation. So the velocity of the thing slash the wave, all right, is going to be how far did it go, the distance divided by the time. And then if you're talking about a wave, the wavelength, right, over here in our picture, the wavelength is the length of one wave, right? So the distance can be a wavelength, so you can switch the distance to this upside down y, also called lambda. The wavelength is lambda, and all of that divided by the time is also velocity. But then if you're thinking about what is frequency, frequency is 1 divided by the period of time, the time of one wave. So if you do 1 divided by the period, which is the same thing as the frequency, you can put the frequency in there and you have the wave equation. This is the velocity of the wave is the frequency of the wave times the wavelength of the wave. So here's our little equation that we're working up to today in our lab. We're comparing the regular velocity that you've been used to using to the wave equation velocity. And with our little mathiness right here, they should be the same, which is the goal of the lab, to get your beginning data equaling your finished data. And then now I'm just going to turn you over here and actually do the lab really fast with you. So important thing in your group, you're going to have a stopwatch and you're going to have a meter stick to measure out the distance. I have my little desk set up to, you can see my legs move because that's the important part about this whole thing. So here we go. All right, so I'm on camera again. Got my stopwatch. The person that is doing the walking is probably going to not be doing the stopwatch, but I'm just here by myself, so I'm doing everything. All right, you're going to do the time it takes to do your distance, which is at least 5 meters. So if you're going to be starting, you're going to be like start, and you're moving along, and the goal is to also be a nice constant velocity when you get to the other point and stop it, but I didn't stop it, so whatever, right? So reset, okay. So you want to count how many steps you do and time how much time it is. So the person who's walking, their job is to count the steps, and then the other group member is going to be the stopwatch timer, and you're going to do it 3 times. And the goal is to be nice and consistent. So you're not going to be all like, you're not going to be changing what you're doing. You're going to be nice and constant the whole time. So I'm at the very edge, and I'm going to like start. 1, 2, 3, 4, 5, 6. I did 6 steps. All right, all the way till right here. All right, you're going to turn that into another thing is how many steps do you take before you repeat? That is going to be when your wavelength starts over, right? One wavelength is how far did you go until you repeated. So for me, I went right, left, right. Uh-oh, that's the same thing again. So I did 2 steps and then I repeated. You take 2 steps before you take another step, right? Or before you start repeating, go ahead and say. All right. So that's one of the things you have to know on the little mathiness. 2 steps is a wavelength. There's the answer. I gave it to you. All righty. The next thing, at the very end of the lab, you have to redo the lab, but you have to stay the same velocity and increase your steps. So it's going to be like, here's your original data. We're going like this, just walking regular. And if I'm going to keep that same velocity and increase my steps, I have to do something different. And I'm going to give you the answer visually, but not tell you what's happening. So I have to increase my frequency and keep the velocity the same. So I'm just gonna start over, right? So I'm here and I go. That was the original again. I just redid the original. Now here's the new one, same velocity, more frequency. I hope I did that pretty well, all right? Hopefully visually you're able to see what I did differently right there. One of the other things later on at the very end talks about the amplitude of your step if you're going to be doing cross country, because I did cross country, yay, cross country, all right? So if you're comparing running to frequency of waves and stuff like that, right? So in cross country, if you're going to be running fast, you want to do a big stride frequently, right? So if you're doing a big stride often, you're going to be going fast, right? More distance per time is going to be very fast. And then in amplitude, you want to be nice and consistent in your running. And then one other crazy thing that you don't see people doing while they're running is having a big amplitude when they're running fast. They're not running like this. If you're trying to do that for a 10K, you're going to run out of energy a lot. So the amplitude of everything matters when you're running. You want to do nice and consistent. If you watch somebody that's running a pro, their head isn't going like this because that's a lot of wasted energy in their running. So I think I've covered everything I need to in understanding the waves. I'm going to actually check this again and I'll just add some comments in there to see what I missed, but I think I got it all. So I hope you guys can do the lab and I'll be back. I just down at track. Regions are in the middle of the day. Here we go. All right. Have a good day, you guys. I'll be back next time.